Okay, so welcome to the crash course. Basically, it's 2400 and solid mechanics is kind of an extension of 1300 and how you can interpret bending moments and shear. So it's very focused on shear, strain, and inertia. Mostly, it's very very geometric. So I'd say that these three courses here, these three topics, so weeks 1 to 3 are actually very formula based. So they're not too, they're really important. So they're really important for every single question. You're going to need to know second moment of area for every single question. And for stress and strain, it applies for most of the questions that you're going to be doing. And these questions are really lengthy. So you have to kind of, in the first 3 weeks, just sit through it and then practice it and get really good at it. The more you do it, then the faster it will be. And then the more in the later questions, you'll know exactly what you need to look for. So you'll know what steps you need to skip, and what you actually just need to get the question done. And then the rest of these, so points 3, 4, 5, 6, 7, these are actually the more theoretical parts of the course. So they will be more about how solids is like basically a beam or like a shape, how they'll deform, how they'll react to certain forces, and in what way they will change. So let's go with what is solid mechanics. If you guys know, it's basically like the whole thing about civil engineering and structural engineering. Capacity overloading is one of the most critical things. So obviously, if your capacity is going to be like less than your loading, then your building's going to fail, right? So you want your capacity and your loading to be in mind that the loading won't make the structure fail. So this comes from, capacity comes from geometric properties, which are going to be explained in this course. And if you guys have you guys done Maths 1101? So it's a combination of geometric and material properties. So what material properties mean is basically like what material you're working with. In civil, it's mostly steel, concrete, and timber. And this is, you'll have a better understanding if you've done Maths 1101. This is just it's a chemical engineering and a material science course. If you did it in term 3 last year, it will make a bit more sense. So that's more about like what is the material capable of. And then loading is going to be how much can be loaded. So this will be more familiar. This is going to be your shear diagrams and your bending diagrams. So if you remember, like for a simple beam, it looks kind of like this. If you have a beam that's kind of like that, and then you have the force. You guys agree? And then for bending, it looks a bit more like a triangle for this particular case, right? So that is all done in ENGG2400, which you guys would have all done if you were here. And then loading also considers stress and strain. So these are new concepts that are going to be explored in ENGG2400. And it's basically what makes up, so we're going to be focusing on these 2 points in particular in this course, and they are going to be more like add-ons to 1300, geometric properties is going to be completely new for you guys. So these are just some general engineering drawings, just to get you familiar with what kind of terminology people use in terms of dimensions. So we refer to the breadth as this longer part. The length is usually the length of the whole beam. So if I was taking this cross-section here, this cross-section, mostly for cross-sections we look at the breadth and then here the depth, so this one. But then the length is usually just the whole length of the beam. So for example, it would be the length here. This is the length, right? So yeah, you will have to get used to this. This is a plan elevation. This is from the top. This is from the side. And then this is just from the other side. So you guys kind of get that? Yeah? No questions? Cool. So now let's move on to second moment of area. Second moment of area has a lot of formulas that you kind of need to remember and then you need to apply. So when you're looking at a prismatic beam, or any beam to be exact, this axis here is called the centroidal axis. And do you guys want to have a guess at what centroid, like a centroid is?
0 point? The center of mass?
Yeah, center of mass is a good way to put it. So, for example, like this would be the centroid, and like this would be the centroid. For a triangle, for example, where would the center be roughly? Yeah, so around 2/3 of the way down from where the thick part is, right? That's pretty much the idea of centroid. This centroidal axis can pretty much be put. So if you see these blue lines, right? You can put it anywhere you want. So this can be put like here if you really want to, here, or like straight in the middle if you want. And that's a bit better. I'll explain it when we get to composite shapes. It's a bit more of a kind of a preference thing. So I'll explain it when we get there, but I'll go over what centroid actually is for you guys. So to calculate a centroid, basically, this is denoted by a little x hat or x bar, usually. And then for the y centroid, it's going to be a y bar. So these are actually coordinates. And so when you calculate a centroid, you'll usually give your centroid, like centroid is at these coordinates, and then it'll be that. Something like this, pretty much. And that will be where x bar is from the distance of the center of your centroidal axis. And then y will be the distance from your y-axis. So, for example, that will be x bar and that will be y bar. Yep. And this formula just means this is the distance of, let's say I is the amount of shapes you have. So this will be on composite shapes, and A is going to be the area of one shape. So in this example, we have one shape, so we can just say that there's only going to be one area, right? So we can just say that we can just find the x-axis, the centroid of the x, by taking half of the square and rectangle, because that's what the center of it is. And then it's the same for the y. It'll make a bit more sense when we do composite. So,
some area on the bottom of y.
Yes, there is. Yeah. First moment of area is pretty much the second kind of step into moment of inertia. We don't really use this much into the course. It's more like a fundamental understanding. So this is actually this is actually known as like the moment of a shape. It's a bit weird to understand, but it's you don't even really use it too much at this point. It's only used in more torque and torsion, which will be talked about later. But don't really worry about this one. It's not too important right now. Now, the part where it's a little bit more confusing is the second moment of area. And these are just formulas that you have to know and get to know. just formulas you need to get to know. The second moment of area changes for both x and y. You guys will notice that there's going to be a little cubed part, and it's going to change depending on which dimension you're looking at. So if I was to draw a cross section, and this is B, this is D, then your moment of inertia around the x-axis, which would be how well it can take forces along the depth. So, yeah. And then if you're rotating around this point and there's a force this way, then will it be stronger? Okay, actually, a better way to explain it is, if you have a thinner beam, this is D, this is B, and let's say you were to squish it from the top, which way would be stronger? Oh, sorry. If you were to squish it from either the sides or from the top and the bottom, which way would fail first?
Is it secure?
Just like if you were to compress it.
From the top.
Oh, actually, wait, no, sorry. If you were to just put one force into it.
The place where you put the force.
Yeah. So, wait, no. So if you're punching, let's say you're punching a plank, and you're punching it from the shorter side as opposed to the longer side. Which side will break?
The longest side.
The longer side. So it just means that it will have a stronger moment of inertia, internal moment of inertia around. This is weird to explain. Essentially, if you're punching it along the x-axis, then the depth will be stronger, right? So that's why you multiply it by itself 3 times, and then for the y-axis, it's the opposite way. So the breadth will be stronger. And then you divide it by 12. This is the internal moment, internal inertia. And this part here is called the parallel axis theorem. And this is only for shifts, particularly when you have a centroid and composite shapes is more when it's used particularly. And you guys have seen the parallel axis theorem in 1300? Yeah? So it's kind of similar. This is just the...
Sorry, that's when you move the moment of inertia.
Yeah, so basically, if you have a shape that is, let's say we have a T-beam,
Yep.
then the centroid will roughly be closer to the flange.
Yep.
Then, let's say, because these are going to have these two shapes, shape 1 and shape 2, are going to have individual centroids, right? You're still rotating, your moment of inertia is still around this point. So let's say you were to apply a force here. It's still going to rotate around this point, you agree?
Yeah.
Yeah. Then, but you can't consider the moment of inertia for shape 1 around this point. So you have to shift it down towards the actual centroid of the whole shape. Yeah. And the product of inertia is the last one you kind of need to learn. It's usually 0 for rectangles, but the only part where it becomes a bit trickier is where you have to shift it as well. This is more you won't really need to use it in a question, but it's good to understand. Essentially, why some shapes have 0 moment of inertia. If you have a rectangle, then you have a centroid, right? So let's say this is your centroid. If you were to take a diagonal, so let's take this diagonal, and then the opposite diagonals. The inertia here should cancel out with the inertia here. It's more of a cross-section thing. This is a cross-section. And you know that it's 0 because all of these sections equal 0 together. So this will equal 0, and then this will equal 0. And you can kind of think about it as well in a T shape. So as we discussed, the centroid will be about closer to the flange of the height, and your centroid will create an axis like this. Now, if you do those same kind of markings, then you can say that this is a positive moment of inertia, this is a positive moment of inertia, this is a negative moment, and this is a negative moment, and all of this will sum to 0. Pretty much. That's the product of inertia, and when the product of inertia is uneven, that's when you tend to get more the rotational failures in your beam. Yeah, so we'll go over an example using all of these formulas now.
I just have a question about the formulas.
Yep.
You mentioned we just sort of have to know it. Does that mean like we have to memorize them, or is it something that'll be in a formula sheet if we have to do an exam? Or
It'll be in the formula sheet, but they're not too hard to memorize. If you understand like the shifting of the parallel axis theorem, and I think these ones are the ones that are most useful to memorize because they help you get through questions really quickly. But X centroid and Y centroid are going to be quite fast the more you practice it. The first part of this course is all practice. So, okay, we'll.
I've got another question.
Yeah.
So, like, you know how you wrote IX earlier in the second mode inertia? What is the difference between IX and IXX?
I wrote them the same thing. So this one, so technically this is actually IX, and then this will be IXX. Yeah, it's just the notation thing. Yeah. Okay, so let's try and find the centroids and moment inertias for this shape. Basically, you have shape 1 and shape 2, and you're going to try and, where would you put the, let's say like you have a centroidal axis. Where do you think I should put this? Yeah, so I had it down here before. Why wouldn't I put it like over here? Yeah, pretty much. Like, you want to try and do as less work as possible, the least amount of work as possible. Another good place to put it is up here, in between all of the shapes. You can put it virtually anywhere, and you'll actually arrive at the same answer. It just means that if you put it down here, your centroid is going to have both x and y values. But if you put it along this x-axis, you'll notice that both of the shapes have the same point of symmetry, right? So in reality, you're actually going to have, you're only going to have a y centroid. So where you put your centroidal axis is actually quite important. In some questions that they give you, they'll give you a centroidal axis, and you just have to work off it. You can't, you can't make it up, and then you have to actually use the one that they give you. So let's find out the centroids. Let's break it down first, and I'll have you guys help me. So let's think about shape 1, and let's think about shape 2. What would, I guess, the values for A and X be for shape 1 and shape 2? So yeah, X will be 0. And shape 2? Oh, okay. I think I get what you mean. So this whole thing is 0? Is what you're saying?
Actually, sure.
Okay, so this whole thing is 0, but why?
Is it because like the axis that you put on?
Yeah.
It's just straight up.
So if you think about this, the centroid of this shape is going to be around here, around the halfway points of the rectangles, right? And this x centroid is already sitting on the x-axis. So if you think about this, it's going to be a area of 1 times 0 plus area of 2 times 0 over some area. And this is just 0. So that's why that's 0. What about the y? The y is a little bit more involved. So it will be up around halfway here. So that will be for y2. And then all the way up to shape 1, which would be y1.
Do we use millimeters for this or meters?
That depends. So you can use millimeters, meters, and typically you'll learn about the stress part, but we go for newtons and MPa, or kilonewtons and kPa. And those are the easy conversions, yeah. But in this example, we're just finding millimeters, So what would y2 and y1 be?
125 mils.
Yeah, this is 125. And then y1? Not quite.
275.
275. Good, very good. Okay, so shape 1 will have the area of 300 times 50, correct? Yep, so it'll be, we'll put 300 times 50 times x, which for shape 1 is 275, right? And then we'll add shape 2, which will be the area, which is 50 times 250, the breadth times the height, and then times 125, right? And basically that's like the location. So you're pretty much weighing how much a shape is and then measuring how far it is from your distance. So then you can actually find the centroid. Because some parts are going to be beefier than others in terms of their rotational axis, right? Another way of thinking about centroid is rotational axis. Yeah. And this will be all over the total area, which will be 300 times 50 plus 50 times 250. And you get, if you plug this in, you get 206.818 millimeters. And that means that your centroid coordinates is equal to 0 and 206.818. So that means that the centroid is about here, right here, and that this distance is your y bar, 206, right? Okay, so now that we found that, we'll find the y moment of inertia around the y-axis and the x-axis. So again, you do this for shape 1 and shape 2. Now, most of the time you're going to be using x, but it's a good idea to just familiarize yourself with when you're going to be using the b cubed or the d cubed. So let's just do this. What would the values for these ones be?
B would be 300.
Yep, correct. And then the other one will be 50 over 12. And then this one will be the other way around. So it'll be 50, right? Now, 250. Why don't I need to use the parallel axis theorem in this case? Sorry? Yeah, so we haven't shifted it at all. Both of the centroids lie on the exact same axis as the x-axis, right? On the x centroid axis. So we don't actually need to shift either of the shapes at all, which is why we can just use the first part of the equation. So that after you calculate it, it will be 1.151 times around 10 to the 8 millimeters quartic. You have to know that this is always going to be a quartic. If your moment of inertia is not a quartic, then you've done something wrong. And typically, this number will be around 6 to 7 to 8. Yeah, it will be a big number if you're doing it in millimeters. Okay, let's do it for the x then. So in this case, we can just take the one that we see above. So for shape 1, let's take 300 times 50 cubed, 12. And now let's shift it. So we'll take the area, which is going to be 300 times 50. And what will this shift look like? So this is, in this example, is y1. And then this is the actual y centroid. So essentially we're finding the distance from here to here. Oh, I'll try and, yeah, this distance here. So yeah, we can just generalize it though. So you say 69?
I think so.
So 275 minus 206 roughly, right?
Yeah.
Squared is around 69.
That is 69, right? Am I tripping?
Yeah. You're
oh
right.
my god.
Okay, so that's for shape 1, and then for shape 2 you do the exact same thing, except you take y2 instead of y1, and that'll be the distance. That'll be the distance here. And to be honest, where you can actually interchange these. It doesn't matter because it's squared anyway. It's still going to yield the same result. If you want consistency and just getting used to it, then just do it one way or the other. Yeah. And after you do all of that, for the second shape, you should get something that looks around like 2.268 times 10 to the 8. So they're quite similar, right? Quite similar numbers. And the product of inertia is, if you guys remember, what is it going to be? 0, correct. And that's because of the T-shape thing earlier. So we have a T-shape here, and this T-shape is going to have no product of inertia. Yep. Okay, cool. So I didn't know whether or not to do this separately, but I think I'll just do it as the topics go. So this is week 3. So we're jumping from week 1 to week 3. This is the introduction of Mohr's circle. So Mohr's circle is essentially the super visualization of how shapes interact with both inertia, shear, and strain. It's quite overwhelming to look at first, but if you guys have any questions about it, then you can just ask me. Basically, for a moment of inertia within a shape, it will have the values that we've depicted, which is going to be Ix and Iy, right? And Ixy. Now, if Ixy is 0, then that means that your Ix values and Iy values actually sit here, and they will be the maximum and minimum. Sorry, X. and they will be the maximum and minimum, right? So that's only for the case at which you have IXY where that isn't 0, and that will be only if you have a shift in your product of inertia. There's an example in the slides, but I feel like I can't really explain it too well. So maybe you guys can look at the slides and then it will click a bit better. And if you do have a product of inertia, there will always be a principal angle. So let's say that you had a shape that looks somewhat like this, a bit wonky, right? A bit wonky. The centroid will probably sit somewhere around here, and that obviously doesn't have like a product of inertia where it's 0, right? Now, what this principal angle is saying if we were to rotate this, at what point would this shape have a product of inertia that is 0? So you're trying to basically find the Imax, the inertia, the maximum inertia and minimum inertia that a shape can handle. But that's only for an irregular shape like this. You'll rarely see it, but it does come up sometimes. And that is basically what it just means. So these are your formulae for those respective elements. This is just the center of the circle, and this is the radius by Pythagoras. Yep. And then you have a transformation. So that's when you want to rotate a shape. Let's bring our T shape back. That's when you want to rotate it by a certain angle. And by doing that, you basically have an angle involved in your inertia, and it's basically doing the principal rotational shift but backwards. And there are a bunch of formulas that are assigned with it. So I probably won't go into this into detail because it's not something I can explain well. But there is also something you should know. A rotation on a shape means that it's going to be double on the Mohr circle. Why? I think it has to do with how the shape moves around. Like it will, some sort of rotational symmetry axis. I'm actually not completely sure, but it just is too. And for inertia particularly, you can note this down. For inertia, it will rotate counterclockwise. So you'll find later that on the shear and strain, the shear and strain, it will rotate counterclockwise, which confused a lot of people when we were doing this course. So just make a note of that, and then you can go back to it and know what is right. Okay, let's move on to topic 2.
Just quickly, are there any applications for Mohr circle?
I think in a more detailed application, yes. It's meant to be an overview of a perfect overview of how a shape moves in every single scenario. If you were to take the angle and then move it around even more, then where would this line sit? It would probably sit probably sit this or something, where it goes all the way around there, and then this will be your new values that you have for that current orientation of the shape. Yeah, it's a bit to go through, but it's meant to cover every single possible thing for the shape. Yeah. Okay, let's go over some shear and strain. So if you guys have done maths, then this might make more sense to you. These are more material properties for now. Actually, wait, no, sorry. this one is a material property. You guys have probably heard of elastic modulus before. Elastic modulus is basically the stiffness of the shape. So stiffness is basically how strong it is under pressure. Steel, for example, is more stiff than like a wood or like a rubber, right? If it's a lower elastic modulus, then it actually is more elastic. Yeah. So the higher the elastic modulus, then the less it can stretch, pretty much. Yeah. And stress and strain. So stress is pretty much is like a formula over force. If you think about it in a way, it's like where you have a force applied, and when you apply a force, it will spread across the surface, right? So, yeah, it will spread across the surface, and that's why the stress is going to be that force divided by the area that it's applied on. So this, for example, this area over here, the stress will be that force spread along that area. So it will kind of look more like this, where it's all over the shop, like that, and then all of that is your stress, pretty much. Yeah. And your strain is mostly visualized by the elongation. We can also call this change E, which is known as elongation. That's basically when you pull something. So when something gets pulled away, like how it is drawn in here, so like this, then how much will it stretch? If it's being compressed instead, like this, then how much will it squish? So that's your elongation and your strain. And then the elastic modulus is the material property that makes up both stress and strain. So you'll see a lot of diagrams of materials. They usually have a stress-strain diagram, like this, and then they might look something like that. It's just a material property thing, and we'll go into that a bit later. Then you have the shear and tangential stress. So this is called axial normal. You can refer to it as normal. It's just along the axis. And then shear will be like acting upon an area. So you can think of normal as normal to the area, to the surface, and then tangential will be like along it. So you can kind of think about two pieces of paper as well. Like if you poke it, then it's going to go through, right? But if you slide them against each other, that's gonna shear. Yeah. And those are the same concepts. So we have shear stress, shear strain, and then we also have a shear modulus. This is the same formula as the sigma, but it's just in a different context because it's in a shear context. Yeah. They're pretty much identical, they just mean different things in terms of what force is being applied. Okay, so to help you get an understanding of what stress actually is, we're gonna go over this question. It's basically, you find the length of D such that the stress in rod AB, which is this one, and rod CD, which is this one, is going to equal the same thing. Yeah. So, do you guys have any first thoughts? What will we put into here? Yeah, so tension is a force, right? We put the tension in rod AB. This tension in AB. And then, what would that equal then? Yeah, sigma A, which is just going to be 12 millimeters times times 10 to the negative 6. It's going to be roughly 4 zeros. Yeah. Sorry, meters squared. Because we're going to convert it to meters, right? So this is in millimeters squared. We're going to convert it to meters. So we're going to stick to those units. That's why I've multiplied it by 10 to the negative 6. Okay. And then for TCD, it's the same thing. It's just that, except you'll get something along the lines of 0.00008. So this is 0.0008 meters squared. Okay. So now we know what those values are. This is 12 times 10 to the negative 6. This is 8 times 10 to the negative 6. Okay. Now you could just use 1300 here. 1300 is just going to be the forces in the y direction. And you'll get TAB plus TCD minus 6 is equal to 0. And you arrive at 10 times 10 negative 6 sigma plus 12 times 10 negative 6 sigma minus 6 equal to 0. And then sigma ends up equaling around this kPa. So that's how stress is distributed among a beam, pretty much. It's kind of a more tension example, but this example just shows you how force is converted into stress. So because stress is a concept that is not clear at first, I think, particularly in how it's taught. So now we can find the distance. We know both of these values and the distance. So now if you take the moment at A, you can get something that looks like 6 times d. Negative 6. So we're taking this moment. Negative 6 times d plus TCD times 3 meters. And that's just 1300. This will be d is equal to 1.2 meters. You'll find. This is, this is 8 times 10 negative 6 times 0. And you'll get 1.2 meters if you input that into a calculator. So that's pretty much the conversion of stress. Now let's look at what stress actually kind of is. So this is called the stress element. This is called a 3D stress element. Basically, if you're looking at this plane, let's look at this front plane first, right? Then means you have a shear element. So this is a shear stress. This is along the face of the cube. Then you have 2 more stresses that are going to be, you have one that's away, and that's going to be your axial stress, right? So there'll be 2 shear stresses and 1 axial stress along every single plane of the cube. But in this course, just for simplicity, we're going to look at 2D element. And what this looks like, in the 3D element, in anywhere in the beam, this element can be anywhere. So for example, if you have a load on this particular beam, then the stress at a point down here, and like this is on a microscopic level, right? The stress here will be completely different to the one over here in every single way. So that's because the beam will deflect like this, right? It will kind of bend down on a microscopic level, and then each individual molecule is experiencing a different type of stress, yeah, and shear. So that's kind of what the stress element is. Do you guys get that part? Yeah. Good way to think about it is in soil. Like each grain is different, and the way that each grain has stress, because they build on each other, right? So they grind against each other. A lot of grains grind against each other, and then that, like, you can think about that as like an individual stress element. Yeah. So this is kind of generally what we are looking at. This is the 2D stress element, and this is how it's portrayed. So your Y stresses, so you can have an axial Y stress and an axial X stress. So those are the ones that are going to be pulling and pulling or pushing against, and then your shear stresses are the ones that go across the face. So those ones are typically denoted as positive if they're pointing in the top right or the bottom left. If they're going this way, then it tends to be negative. And that's just the notation. Yeah. Okay. Just remove those. Now, this is back to Mohr's circle. Mohr's circle is a bit more applied in stress and strain. Most of the time, you're going to get given a question where you are given an element. You're given an element such as this one, except it's not going to be perfectly aligned. So, give you an example here. If you're, actually wait, I'll explain this first. Let's say you get given this stress element here, right? And then they ask you to rotate it by a certain amount of degrees theta. Then this blue line is going to be the first. This blue line is going to be the first, the first stress element. And then when you rotate it, you're actually going to rotate it by 2 degrees theta the clockwise way. So it is opposite to the inertia, Mohr circle, and it's just how it is. I can't really explain it in another way. I think it's just how it is. And essentially, that's the transformation of stress. So that's when you're rotating it. These points here, the stress 2 and the stress 1, do you guys remember when I was talking about your your maximum and minimum moments of inertia? So that's essentially going to be the, they're like the equivalent of the maximum minimum, but they're not really maximum minimum. They're called the principal stresses. Actually, yes, they are. They are. You can think of them as minimum and maximum. They're called the principal stresses, and they'll always be sitting on the x-axis because they're at the very extremes of the circle. Right? So this is your stress values, and then your shear values sit here. So what it's kind of saying is when your shears are at its maximum, then it's when your stresses are at its maximum, then your stress element isn't going to shear at all, right? Like, because there's no other force that is being applied to the stress element in the opposite direction. So it can't shear in any way. Yeah. And that is the transformation. So those are some of the values that I've written out. For example, this is going to be for a principal plane, and then this is going to be the rotational by theta. Okay. Maybe it's better if we do a question. So let's say at a certain point on the surface of structure, following stresses are known, and you have sigma x is 12.2 MPa, and sigma y is negative 9.2 MPa. And then the tau xy is negative 21.1 MPa. So how would you guys draw this on the stress element?
Sigma x going sideways.
Yeah, like this. And this will be 15.2, right? How would you guys draw the rest of it? Is it going into or outside, out of the? So this one's actually going into. So if it's negative, it's actually compressing it. Yeah, so this will be negative 9.2. And then the last part, which is the shear. How would you denote the shear?
Negative, so you go top left one.
Yes, correct. So it will look like this. And you'll get negative 21.1 MPa. Oh, sorry, yeah. Now, your principal stresses, if you remember the Mohr circle part, you can find the center. And a good thing to note as well is that x plus y over 2 is equal to 1 plus 2 over, yes, over 2. So the center is going to be the same for both of, yeah, wait, let me visualize it for you guys. So basically this point and this point, right? Let's say that's the points we're looking at on the stress element. That's how much the stress element is experiencing. So in this case, it's going to be negative 9.2 and 15.2. Let's say, yeah.
1300 is compression is positive.
Compression is in tension. Compression is negative in 1300. Tension is outlay. So if you think about like a joint, right? These ones are in tension. Oh, sorry, yeah. These are in tension and these are in compression. Yeah.
Compression is positive.
No, compression is negative. So this is negative. That's because it's compressing the joint, and then the tension is pulling it away. Yeah. Yeah. In most of the courses, tension is positive. Yeah. Okay. So, yeah, you'll notice that the center of these 2 points are going to be the same as the center of these 2 points, right? Like all of these have the same center. These two have the same x, and then these two have the same x, and then it will both sit horizontally parallel. So you can kind of think of this as the center plus the radius of the circle, which is something like this. And then you get 27.37 minus 21.37 MPa. Okay. MPa. So yeah, on the Mohr circle, this kind of looks like what this is. This negative. Kind of looks like this. This is 9.2. This is 15.2. Oh, sorry, wait, no, that's wrong. This is this is negative 21.1 MPa. Oh, sorry, god damn it. 15.2, 21.1. And then this is actually negative 9.2, 15.21.1. This is your shear. This is your stress. Do you guys understand how I got to this? This on the Mohr circle? And then your maximum principal stresses, this will be 27.37, and this will be negative 21.37. Do you guys get it? Yeah? So what this question is actually saying is that this whole diagram is actually not straight. This whole diagram has actually been rotated, essentially, which is why it's experiencing shear. But they just draw it in a way that it looks straight, so you can understand it a bit better. Now, when it asks you to find the principal, values and the principal angle, it's asking you to find the angle at which you rotate it so that it is straight. So if you were to rotate this backwards, down, this is called the principal angle. And then to get that straight, that's when this will start looking like this. This will be 27.37, and then this will be negative 21.37, right? And then the stress element isn't actually experiencing shear anymore. So to find that angle, use this formula. And then this will equal negative 1.73. And then when you put the tan over and then divide by 2, you get something that's like negative 29.98 degrees. So this is actually a, this angle, P, is actually 29.98 degrees. And then on the Mohr circle, it will go the other direction. So if it's going clockwise on the stress element, it's going to go anti-clockwise on the Mohr circle, right? So it's going to actually be going this way, and you can see that the drawing is correct. And this is 2p, 2 theta principal. Mohr circle is a little bit confusing. Do you guys get the Mohr circle a little bit there?
Why did you draw like the two positive numbers and like the negative region?
Which one?
Like either 15.2 and 21.1.
Oh, this is positive 15.2 and that's negative 21.1. Yeah. So that's how that question is kind of shown on the Mohr circle. You don't actually need the Mohr circle. You only need it to do like all of this stuff. But I was just showing you how it works on the Mohr circle. Okay. Now let's go to strain. Strain is pretty much the same concept as stress. So it's it's different in the way at which stress is the force at which is being enacted onto a shape. Strain is the result of that force. So when you pull something, let's say you pull like elastic, then it's going to get thinner and thinner, but it's going to get longer and longer, and it will be like that on both axes. So that's what this is saying. Shearing the strain is essentially going to squish both on both axes, and it's going to make it thinner along. How do I explain that? It's just a shear version of the strain. So it's going to be the result of the shear. If you're shearing it like how you're shearing, you can kind of think about if you're going to shear this element, then you're going to be pushing it up in that direction, right? Then that's what this deformation is going to look like. This one over here. Okay? And those are just some like examples of what that will be on the actual diagram. And essentially, yeah. I need to check that that's right. Yeah. Essentially, the stress and strain formulas are interchangeable. So you would notice that these formulas are actually like identical to the ones up here. The only difference is that there's a -2 here, and there'll be just a regular negative for the shear strain. That's because for some reason the shear strain is denoted by over half, and not exactly sure why. That's the only difference. All the Mohr circle transformations are the exact same. So it's something that you have to think about when you're doing stress as well. Yeah. Okay, running low on time-ish. Actually, no, I think we're going okay. Let's go into the more theoretical stuff. So that's the more formula crunch stuff. It's just something that you have to get really used to. I know that for inertia, at least, for inertia, a good way to do inertia questions is to just pull out a table. Pull out a table and just say like, this is shape 1, shape 2, this is B, this is D, this is, this is the area, this is the, you'll find the centroid somewhere else, and then you can find your dx, which is your x minus x bar, and then you can find your dy, and then you can find your ix, and then your iyy. And then that way is just a really simple visual way of doing it, because after this, you actually have to, like where this is BD cubed on 12, this is B cubed D on 12, and later when you finish the table, you can actually just sum it all together, and then you can add it. So that's a really quicker way to do it. It's really easy to Excel, so there actually are a lot of Excel sheets out there that just do it for you. But okay, let's go into the more theoretical stuff. This is the more theoretical stuff and the more applied versions of this. Applies all of the inertia, stress, and strain. So that's why it's really important to get the basics down for those ones. Axial deformation. So axial deformation is essentially just if you pull something or squish something, how much will it change? That's particularly useful for that's particularly useful for beams and tension. Yeah. So when you're putting a force onto a surface, then it's going to change, right? Like it's going to elongate by a certain amount. Let's say, no matter how small it is, it's still going to elongate a slight bit. That's pretty easy to understand. This is the elongation. This is the formula for the elongation. It's going to be the force times the length, and then over the Young's modulus, and then over the sectional area, cross-sectional area. Yeah. Do you guys have any questions so far? No? Okay. So now, what happens if we change it? What happens if you have a shape that like looks something like this? What do you guys think happens? And this is like a, this is like a length that changes.
The area changes.
Yeah, so the area changes. Does anything else change? Technically, the length doesn't actually change. So the area is the only thing that changes. That means what else changes if the area changes? You can think about further back as well.
Centroid. Is that what's called?
No.
The lowercase e.
So yeah, that's the result. You can think about further back to inertia, stress, strain. So what will change is, sorry? No. Okay, so what will change is these cross sections are different, right? As was mentioned. That means that the stress is changing, right? If area is changing, that means the stress is changing. And this this means like how can we calculate stress for an irregular shape? It's essentially going to be put into an integral, which isn't too important for you guys to remember. I don't think I've ever seen a question with irregular shapes. Just kind of good to know. FL over E. So that's just that area. Since your area is the only one changing, you just have to put it into you just have to find an equation that changes with X, and then it will change according to that. So that's the elongation for irregular shapes. That's for non-discrete. That's for non-discrete shapes. When it's discrete, they'll put it like this. This is actually a workshop example in your in week 5. So what do you guys think happens to a composite shape? If you had something that looks like this, then let's take it at a surface level. For the first level, like level 1, level 2, level 3. What do you guys think will happen at each level if this is the formula? You can think of it as elongation is equal to flee. It's a good way to kind of remember it. What do you guys think will happen?
Level 1, which is the top one.
Yeah. It is equal to F1, L1 over E81, right? What about level 2? Which one? What about level 1 and 2? So the only thing that will change is that the force on both of them add up. Because when this is experiencing a stress, this level here, then it's also putting that stress onto the second floor. So that means that it's actually going to add up, except the area at which the second floor is experiencing stress is only on that cross-sectional area. So if I were to take this and cut it, so this is level 1, then let's take this, and then let's cut it here, right? If you were to think of a point at which this is F1 and this is F2, oops, sorry. F1, F2. Then the cross-section here, right, is going to be the cross-section of area 2, right? But it's still experiencing load 1 and load 2. So it's going to take on both forces, but it's only going to be elongated by the second. Actually, I need to check that. Oh. Oh yeah. It will just change by that amount. So it's pretty much only the force that changes according to composite shapes, and then for level 3, it's just going to be the same thing. Right? Okay. Let's go into the more fun stuff. So this is how stress and strain is kind of more visualized inside of a beam. This is called bending. So you guys kind of already know a little bit about bending, just like how stuff bends, but I guess you don't really know yet about why it happens or how it happens. So you already know that if you have a beam that's a simply supported beam that has a point load in the middle, then the shear will look like this. This is the shear, and this was the bending. So in civil engineering as well, it's more common to draw the bending moment positive on the negative side. So mechanical or other disciplines might put the bending here as a positive side because it just makes more sense. For us and civil engineering, it makes more sense to put on the bottom because it's kind of showing how the beam is going to bend in that way, right? Like if you were to see this beam, it will bend kind of like that rather than like, concave up. So, now, when it bends, what is going to happen is essentially these top parts are going to compress into each other, right? So on a micro level, the top part of the beam is actually going to push into each other because it's bending like that, right? So it's actually going to be compressed. And then on the bottom side of the beam, it's actually going to be the opposite way. So it's actually going to start tensing up. So this is in tension. You guys can visualize that, right?
Yeah.
Yeah? Okay, now why this is important is basically on the cross section of a beam, let's say this is a regular prismatic beam. And that's our cross section. Basically at your y centroid, you have your neutral axis. See your neutral axis? And the neutral axis is where the shear that the beam experiences is 0. So the stress that the cross section experiences is 0. So if we were to graph the strain, then it would look something like this. This is like a positive strain. And then this is a negative strain, right? And let's just this is going to be equal among the entire beam. Now we have the stress of the beam. Can you guys imagine how this would look? If the elastic modulus is just stress over strain, strain, then you get this. What do you guys think?
Just times by constant.
Yeah, so it's going to look the exact same. Just a little bit bigger, a little bit smaller, depending on what the elastic modulus is. Typically, this will mean that this is in, if you're drawing it this way and the top is compressed, then this will be in compression, this will be in tension, and this is your point of 0. So it's actually positive, this is negative, right? And to be brought further in, when this is called the flexural formula, and it's useful for finding the point of stress at a certain point in your beam bending. So you can agree that when the beam is at its halfway mark, it's at its most critical moment, right? So this is where it's bending the most, essentially, right? If your point load is at the center of the beam, then it's going to be bending there the most, correct? So this formula is actually just saying at a certain moment, at a certain point in the beam, it's going to be bending differently, and the moment of inertia as well stays constant because that's a geometric property. The y, which is the depth from the neutral axis, only matters when it's when the shape of the stress is not regular. So you don't really have to worry about it in this example, but what I mean by the moment changing from point to point in the beam, you agree that this is F, and then at this point, let's just visualize the stress here, right? The stress at this certain point is going to be massive. It's going to be M max, correct? And this is going to be multiplied by all this junk. And that will be the stress at the center of the beam. Now, let's say if we took to point A over here, right? Now, this is actually going to be experiencing a different moment. It'll be a bit less because it's closer to the pin joint, and it's going to be experiencing something like this. Now this is still in tension, and this is still in compression. This is still in compression, and this is still in tension. It's just the magnitude of it is more, is smaller because of the moment in A, right? So that's more of a generalization of stress. And that also helps explain the stress element and how each point inside of the beam is different to each other. Yeah. So as well as like you can also visualize like this point will be different to this point, and then like you can think of that as a stress element. You can think of this as a stress element. You can think of this as a stress element. You can think of this as a stress element. Okay. Any questions so far? No? This is the cool part of the course. Okay, so elastic versus inelastic bending. This is a bit more materials focused. Do you guys have an idea of like plastic and elastic materials? Okay, so let's take an example of steel. Steel has a property where it will be as strong as it likes up until a certain point. So when you strain it and strain it and strain it and strain it and strain it, it will eventually yield. So that's not, yielding doesn't mean breaking or failing. It just means that it will change. So let's say this, in this point in the graph, it will stay constant. It will stay constant the more you strain it. So the more strain you add to it, then the higher the stress will be. And that is what it can withstand. That is called the elastic region. And basically, this is strain of Y, and let's say that this is this for yield, Y for yield, okay? Now, what happens with steel is that it will actually kind of look, in a more general sense, it will look like this after it is yielded. So it will actually take on less stress as you put more strain on it. But that's because it's deforming while it's being strained. So this is the point at which it starts deforming. And then eventually it will come back down, and then it will break. So this is the breaking point. And then all of this section is called the plastic region. Yep. And cool thing about the plastic region as well is that after it has entered the plastic region, it can never go back to the elastic region. So once it's been broken, if you decide to remove all the strain that's been put onto the steel, then it will go back, but it won't ever be as strong as it usually was. So once you strain steel enough, then it won't return to its normal strength. Okay, so let's think about elastic, partially inelastic, and inelastic materials. In terms of steel, when it's elastic, we have our usual stress kind of distribution. So it'll look something like this, where this is, let's just say that this is tension, because I'm used to that, it's tension, and that's compression, right? Now, when it's partially inelastic, is when you're yielding the steel, and the steel has partially yielded. So what happens is when you have a block of steel, then as it bends and bends, so this top part will be under compression, this bottom part will be under tension as a normal beam. That means that these parts, the top parts and the bottom parts, will fail faster than the middle parts, right? So that means that once it has reached a maximum stress, it won't ever leave that stress. So your stress distribution actually looks kind of like this, where this is a separation barrier for both of your steels. This is going to be your elastic steel, which is your strong steel, and this is your plastic steel. Yeah, and then if you keep on straining it, what do you guys think will happen to the stress distribution? Yeah, exactly. So it'll keep going, and then it will turn into something that looks like this, right? Nice. And that's considered fully plastic or fully inelastic. And that is why that happens. So if you keep yielding it, then it will get more and more plastic. That's just an example for steel. If more brittle materials, you'll find that they just fail, and the stress distribution curve can look something like where like this, and then it starts and stops, and then it will just completely break. So there will be no stress experiencing there because there's nothing there to experience that stress. That's a more brittle example. That could be for glass, for concrete. Yeah. Okay. So this is also how you can calculate resultant forces and internal bending moments. What this is basically saying is, you guys remember how stress is another form of force? It's just the force that's been distributed among the entire area, right? These two forces are on the neutral axis. So this is the neutral axis. You can take this entire area. This is going to be the stress. Take the entire area of the triangle and take a moment around the neutral axis. What do you guys think is happening? So this is a cross section. Now, let's say you had the beam. That's the cross section, right? And then you had that distribution across it. Then what is happening? Yeah, so this is literally the internal bending moment at any point in a beam. If we go back up here, this area and this area denote what MA is going to be and what M max is going to be. That's the cool part, right? You can find the internal bending moment for anything if you use this method, and it actually was used in the exam last year to find a plastic moment, so you might want to think about it a little bit as well. But that's the cool part. It's pretty cool. Okay, so now we move on to composite bending. Composite bending is more materials focused as well. Pretty much it's the exact same as how you would find all the answers for most of these other questions for bending, except the thing about composite materials is that you have to convert all of them to the same material. You can't actually consider them all as different materials. So what you do is you convert it into a modular ratio n. Modular ratio n is essentially just changing it into the same thing, but that's because the elastic moduli are actually interchangeable in a ratio that you can calculate the central. You can calculate the strength of it with the same material in mind. You just have to consider that it is going to be a different material. So, for example, if we're going to convert steel or timber into one another, then we have to use the modular ratio n. It's going to be the elastic modulus of the material you're using beforehand, and then the elastic modulus of the material you're turning it into. So that n value only changes the breadth. It doesn't. I was under the misconception that sometimes, like, if you have this cross section, then it will shorten and shrink it all. That's wrong. You have to consider that it's going to change only the breadth, and then the height and depth stays the same. So this modular ratio is the value that you multiply the original breadth by. So for example, this will be B here, and then this will be NB. And it'll be either a shortened or more elongated version of the breadth, right? Like if I was to convert this steel into timber, So this is the one that's converted into steel. If I was to convert the steel into timber, it would look probably something like this. Wait. Woo. Woo. Probably looks something like this. And then that's the timber, that's the steel converted into timber. Okay? Now, it's a bit more of a example question. Let's kind of run through it, so because we haven't done an example question in a while, it might show you as well why inertia and stress is important to nail down. So, to find the normal stresses at B and C, you have your elastic modulus of timber and your elastic modulus of steel, and then the internal moment at that certain point is 2 kilonewtons per meter. So we're trying to find the stresses, but let's do step 1 first, which would be to change everything into a consistent material. So what would you guys think? Okay, yeah, you can do it either way if you want. Let's change the timber. Okay, so changing timber to steel. E before, E after. What would this be? It would be 12 over 200. And this is, you don't need to convert this into MPa or kPa, it's just a ratio. So yeah, you don't need to worry about any conversions there. Now, what happens to our shape is that you draw it like this. And now you find this. So this is 20 millimeters. This is going to be 115 millimeters. And then what this is going to be, it's going to be 150 times 12 over 200, right? That's the end conversion. And then this is going to remain at 150 millimeters. Right, you guys agree with me? Yep. So then you have to use this formula. So to find the stresses, you have to use the flexural formula. And then you can kind of think about, what do I need to find? You need to find, first of all, you need to find the moment of inertia. And then you also need to find you need to find the distance, because we've been given m, and we're trying to find the stress. But we can actually find these two values using what we learnt before about the inertia. So what would you guys do in this example? Think about the centroid first. It's okay, so let's find the centroid first then. Because we need to find the moment of inertia, right, of the entire shape. So let's find the centroid first. Centroid up to here for y will be 10 millimeters. And then centroid up to here, this distance, is going to be 75 millimeters, right? And all of that is going to be 95 millimeters. Oh, sorry. All of that is going to be 95. So then you have to go through the whole process of y bar is equal to a1 x1, y1 plus a2 y2 over a, and then you get something that looks like, if they're calling this shape 1, I'm calling this shape 2. This will be, this value comes out to 9 millimeters. So let's convert everything into meters as well. This will be 0.009, and 0.15 plus 0.02, 0.15 all over, oh I should choose 0.95. So this is your x, sorry, y1, this is your a1, correct? This is your a2, .10, 0.01, yeah, and that's your y2. Okay, and then your total area is 0.009, 0.15 plus 0.15, 0.02. Should end up with something that looks like 0.0363638 meters. And that's your y bar. So your y bar actually sits around 30 millimeters up, which is up here. That's your y bar. Y bar. Okay, so that's like using the centroid, and then from the centroid you find the moment of inertia, which you have to use the parallel access theorem in this case for both of those. Yeah, and I'll just skip it. It comes out to this, and this is going to be the moment of inertia around the neutral axis. So this is the neutral axis where what is clutter? This is the neutral axis around where the centroid is of the y centroid, and that's the moment of inertia at which the shape can take. So now we're trying to find the stresses. For stress at point B, so the stress at point B is at the top of where the wood is. Now, you would take the top, very top, which is 150 plus 200, plus 20, which is 170 millimeters. So -2, because of the internal moment. Then 170 minus the y bar. So 0.17 minus 0.03638 all over the moment of inertia, and then you end up getting so this equation will be your stress at point B, but that's while it's still a steel. So you still need to convert it. This will be B, and you need to convert that by the ratio again, and that will be 1.71 MPa. And then for the stress at C, which is down here, they're going to ask you -2, and then sorry. The stress, the centroid, distance from the centroid is going to be just the distance to the bottom. So it's going to be the centroid, pretty much. INA, -2, 7.87 MPa. Now, where it gets kind of confusing is if they ask you a question where, like, if they add point A and D, where it's like here and here, and they're like pretty much microscopically before and after the transition between wood and the steel. Then you have to find the strain first with the elastic modulus, and then convert that stress back to the strain, because both of these materials are going to take on different stresses, and they're capable of taking on different stresses, right? I'll just show you exactly what I mean. Essentially, let's say we have like timber, and then we have a steel portion, right? Stress distribution actually looks something like this. So at the point at which it changes, timber can take a lot less than steel, right? So the steel actually ends up taking a lot of it. And your neutral axis, let's just say it's about here. It's fake, but yeah. And that is actually what happens in a real world scenario, because at this point, this stress here, at the transition point, the stress before and after is going to be vastly different. And that's because the steel can take way more stress than the timber can. And that's why you need to change the ratio by the modular ratio. You change the stress by the modular ratio. So that's just a quick example. We'll move on to deflections. They'll get a bit more brief because they're more like theoretical points. So if you have, let's go back to the simple beam. You have a deflection, then the deflection is basically the displacement of the beam, how it's going to displace in terms of how it's bent. So a good way of drawing a deflection in your mind is how it's going to curve after it's been bent. Usually with this mx, it's going to be like your shear, which is capital V, and then it's going to be your forces, right? And then going further and further down the list, this is your angular slope. So it's the slope at which it bends. It's an angle, and then this is going to be your deflection equation. And EI is just a measure of the rigidity of your material. So E is the elastic modulus, how stiff something is. I is the moment of inertia. These two together basically tells you how much resistance a material has to rotating. In 2303, you have these two values, which is EI and EA. And you'll learn that EI is, if you were to, let's say if this is a cantilever beam, if you were to put a force onto the end of the cantilever, then if the EI is stronger, then it will actually not bend as much. But if the EI was lower, then it will bend a lot more. So it's pretty much the resistance to bending. Now EA is just the opposite version. It's the axial version. So it's how resistant it is to being stretched and being compressed. But you don't need to know that for this course. This is just for you to help you understand what the rigidity actually is. Yeah. Okay. That's pretty much deflection in a nutshell. It's just basically how it looks. When you do a deflection question, you're probably going to have to do the method where you have to find the equation of the moment, and then you have to integrate it twice, which is really annoying. You'll end up with two constants at the end, and you might get some questions with that later on, but to be honest, yeah, you just have to hope. It's a hope with this one. It's a lot of arithmetic. If you're really good at integration, then should be no problem. Okay, let's move on to shear. So for shear, when a beam is bending, essentially it's going to bend, while it's bending, the particles are going to shear against each other, right? To some extent. So as well as that, it's just when a beam experiences shear, how it's going to experience shear. For a normal cross section, which is a rectangular cross section, the shear actually looks something like this. So it actually takes a lot of shear in the middle, right? Like the shear at this point is way lower than at the middle. So as you shear it more, then the middle is going to take most of it. Now let's look at a I-beam. So for the I-beam, it's actually the reason why I-beams are one of the most optimized shapes in engineering. What do you guys think, like, if this is the flange, and then this middle part is the web, what do you guys think is like the reason as to why they exist? So
One defends against shear force, the other defends against axial.
yeah, pretty much. If you think about the shear diagram, the stress diagram, it's going to look kind of like this, I think. Gonna look kind of like this. And it's going to slow down a bit, and then it's going to come back up. Right? That's the stress distribution of an I-beam. It's actually going to slow down, and what that is it actually takes on most of the stresses at the end points, right? Because a normal distribution, the stress is bigger at the end. Now, if you notice for the shear is actually bigger in the middle. So the shear for the I-beam actually looks something like this. And the I-beam is perfectly optimized to handle both shear and bending in the way that it's designed, because the flange can take on all of the bending stress, and then the web can take all of the shearing stress. So there actually is a reason why it's one of the strongest shapes. This is just a general formula that you can use for this shearing. This is the first time in the course at which I've seen the first moment of area actually being used, which is why I said it wasn't too important. You can have a look at it. The width of the X section and the moment of inertia, again, they have appeared. So those ones are the ones that you need to practice again and again. It does appear a lot in the course, and the shear force here is your shear force diagram. So your V of X, and if you have like this situation, it's just the shear force that is enacting at a certain point. So if you take a cut here, then what is the shear force here? And then that will be the shear force you would plug into the equation, pretty much. It's the shear force along the cross section. You guys have any questions about that? Okay, this is the last topic, so maybe I'll do this, and then I'll see if you guys have any questions after about everything else. Torsion is basically the same thing as stress and strain, except it's on a radial plane. So instead of how much you can pull and push something, it's about how much you can twist something. You have the same thing. It's if you have like a pencil, right? Then you can like twist it, and then it will how resistant something is to twisting. And the stress distribution looks a little bit like this. So it's going to be bigger on the ends, and then towards the center, it's actually going to be experiencing the least stress. It's similar to how this is portrayed again. Like this is at its maximum, and then towards the center, it's at its minimum. So that's the kind of way you can think about it. Torsional shear force can be thought of as by this formula. The internal torque in the radius from the center, as well as the polar moment of inertia. So the polar moment of inertia is same as the second moment of inertia, except it's talking in the context of circles. So there are a bunch of formulas for those. Those are usually given, and it's something you can look into in the course as the course goes on. But you can think about it as just the circular version of moment of inertia. Yeah, and essentially it's the same thing as everything else. If you have a look later in more in depth, you'll find that all of these concepts that I've covered, this is stress, this is shear, and this is the torsional shear. They all have a kind of, they're all resultants of another component. So this is, stress is a resultant of strain, and the shear is a resultant of the shearing strain. So shearing strain is denoted by gamma, and both of these are resulting in some sort of measurement which is in millimeters, right? So they're like, these are like what is happening, and what is stress is like what is going, what is the result? Resulting / driving reason. And then this is the actual like visualization / result, physical result. Yeah, and for torsion, it's just the result is just how much it's twisted. That's the main difference. So that's known as an angle, and that is denoted in this little formula. Okay, so there's 3 minutes left, but I think I can give you guys a bit more time. I don't know if you guys, yeah. So do you guys have any questions about anything in general? Yeah.
Like for this course, right, is it mostly in 2D or like 3D?
2D.
2D.
They just get you to think about cross sections mostly in this course, and then if they tell you to think about a beam, a bending moment, it will be mostly along the side view. Yeah. So a lot of okay. Here's the kind of thing. I'd say let's just draw a simple beam. A lot of the bending and like shear maybe. Shear will be on this kind of like view, and then for a lot of stress, this includes force, BMDs, SFDs, stress, inertia, X section. Stress, inertia, and strain will be more on your cross section. I think it's a lot more emphasis on the cross section later on, and it is cooler, in my opinion. But yeah, that's kind of what you can expect. Hello, yes. Oh yeah, and deflection. Yeah, that's mostly the course, I think. There's another piece of topic that I don't really mention. It's this plane stress and plane strain. It's something that gonna have to go over, and failure and buckling. So the reason why I don't go over this, failure is mostly just the capacity overloading thing. All of this talk, and how much like it will fail if it's been exceeded. I don't think it's tested that much in the course. It's more on the core concepts of all of the geometric stuff. But the reason why I skipped plane stress and plane strain is because I'll show you. I'll just use this. So this is the whole topic of plane strain and plane stress. So you'll notice that this is all the axial deformation notes. You have Poisson's ratio, which is a lateral strain, direct strain. It's just the strains of the ratio laterally and unilaterally. And these are the amount of formulas that are associated with this topic. So they're mostly all formulas. They don't get scared by it. They all like relate to each other in some way, and they're all duplicates of each other. So it's because in the stress element, remember how there was 3 planes on the 3D element? It's just talking about how it's different for each single plane and it transfers to another. Yeah, and those are these are probably the formulas that you're going to receive and you probably want to bring into the exam, because these ones get used quite a bit in some of the questions. But yeah, I didn't really want to talk about all the formulas for this because I think it's pretty in your face, and I think it would overload you. So yeah. Otherwise, anything else you guys want to ask? No? You guys want to ask anything? All good?